Hi everyone, this is Hongsheng. I'm going to present my CCGrid paper, a locality sensitive hashing-based approach for federated recommender system. This paper is written by Hongsheng Hu, Jiodobi, Zoran Sosik, Men Liu, Jianbing Zhang, and Xun Zhang. The speaker is Hongsheng, and he comes from Department of ECE, the University of Auckland. In this presentation, I will introduce this paper from 6 aspects. The first aspect is preliminary knowledge. In the first section, I will introduce what is recommender system and what is LSH. The second section is LSH-based recommender system. In the third section, I will introduce the problem of existing LSH-based recommender system. The fourth section is the key part of this presentation. So I will introduce the differential private LSH, which is proposed by us in this paper. Fifth section, I will introduce some experiment results. And in the end, I will discuss and conclude this paper. Okay, now let's review what is recommender system and locality sensitive hash. So recommender system aim to provide suggestions for users on how to select items among a large number of options. So here, this figure is an example of recommender system. So in this picture, we can see there are two guys. The left guy likes eat pizza and salad. And the right guy also like eat pizza and salad. So what if we want to recommend some items to the left people? Because both of the left people and the right people, they both like eating the same thing, so we consider they are very similar. If we know the right person, he likes drink Coca, we can recommend this cola to the left person because they are very similar. So this is the basic concept of how we can recommend item for the user. Locality sensitive hashing, abbreviation as LSH, is an efficient and fast similarity search algorithmic technique that uses hash functions to hash similar input items into the same buckets with high probability. This figure is an illustration of LSH. We can see in the left hashing key space, there are 3 areas: the pink area, the green area, and the blue area. In each area, there are 3 data points, and because they located in the same area, we consider in the hash key space, they are very close. So we can use LSH to hash these data points to the bucket. As we can see, we can use hash functions to hash the 3 data points in the pink area to the bucket 1. And we can hash the 3 data points in the green area to the bucket 3. And we can hash the 3 data points in the blue area to the bucket 4. So now we are going to introduce LSH-based recommender system. So this figure is an example of recommender system. So there are 2 different companies, company A and company B, and there are 2 users, user 1 and user 2. So each user use some services in company A and company B, so which means different companies will have partial data records of each user. So in this picture, like the user 1, the company A has user 1's data of A1 and A2. For company B, this company B has the data B1 and B2 of the user 2. And the user A also has the data A2 of U2. And the company B also has the data B1 of the user 1. So if multiple companies wish to collaboratively build a recommender system, however, user data rights are located in different companies. And due to the regulation and the privacy laws, different companies cannot share the original data to each other. Locality sensitive hash, LSH, can be used to collaboratively build a recommender system. And the key point is to using LSH to build user index and sharing index instead of sharing user record. So here, there is a user, and this user is interested in A1 to AM of the company A. And the user is also interested in the item of B1 to Bn of the company B. So the company A has the data record of a UA, which is we consider UA is a vector. UA is the data record vector of the user A, of the user U in the company A. And UB is the data record vector of the user U located in company B. So each company can use a hash function to hash the vector UA to FAU, which is a hash value. The same, the UA can use multiple hash LSH functions to hash UA and make the hash value vector GAU. And GAU is the user subindex of U of the user U in company A. The same, the company B can construct GBU, which is the user subindex of the user U in company B. So each company of company A and company B can share GAU and GAB to each other without sharing the original user record. So in this way, the original data record is protected by the hash index value. So this method seems very good, but what's the problem of the existing LSH-based recommender system? So as we discussed before, the key idea of privacy preserving in LSH-based recommender system is to share the user index instead of sharing the original user records. However, there are two limitations. The first limitation is using LSH index to preserve privacy of user records has no theoretical guarantee. And the second limitation is more realistic. So the user records can be reconstructed by a malicious attacker if he knows the hash function and the hash index of this record. So this motivates us to design differential private LSH. So before I introduce what is differential private LSH, I will introduce what is differential privacy. So the epsilon local differential privacy is defined as a randomized function f gives epsilon local differential privacy if and only if for any inputs t and t prime in the domain of f. For any output t star of f, we have the probability of ft equals to t star is smaller or equal than exponential epsilon times probability of f t prime equals to t star. So after we know the definition of local differential privacy, so what's the research challenge? The research challenge is how to combine differential privacy and LSH to provide theoretical privacy guarantee for user records. So suppose there is a user record U, which is a vector, and each element of this vector represents a rating score on a movie. To build differential private LS index for U, we follow 3 steps. So the first step is hashing. We calculate the hash value of U using K locality sensitive hashing functions to get the hash signature S. Step 2, perturbation. So for each user's data U and the bits I in the hash signature S, we create a differential private hash signature as prime whose corresponding value Si follows the following probability condition. So if Si equals to 1, so Si prime equals to 1's probability equals to P. If Si equals to 0, the probability of Si equals to 1 is 1 minus P. So for each company, they can independent follows step 1 and step 2 to build the differential private hash signature as prime. So in the step 3, after each company complete step 1 and step 2, they can send the generated hash signature as prime to other companies. So here, this figure shows what is differential private LSH. The true value of this user record vector U, and the first step, we use LSH functions to get the hash signature of this true value vector U. And after we get the hash signature S, we add perturbation to the true hash signature. As we see in this figure, there are some differences between the DP hash signature as prime and the hash signature. The most elements of the hash signature S and the elements of the DP hash signature as prime, they are the same. However, you can see the hash signature S, the first element 0 after perturbation, it becomes 1. And in the eighth element of S is 1. However, after perturbation, it becomes 0. So now I'm going to introduce some experimental results. So we investigate how the differential private LSH-based recommender system performs, and we will compare it with the existing LSH-based recommender system and one classic non-private user Pearson correlation coefficient-based method. Because the differential private LSH is different with the existing LSH, and the differential private LSH add perturbations to the true hash values. So we can imagine the differential private LSH-based recommender system will not perform exactly the same as the LSH-based recommender system. And both LSH-based recommender system and the differential private LSH-based system will not better than the non-private UPCC method. This is because the UPCC method can get access to the raw data, where LSH-based and the differential private LSH-based method can only use the LSH index without access to the raw data. So we consider two evaluation metrics. So one is recommendation accuracy, and the accuracy is evaluated by the mean absolute LMAE and the root mean square LRMSE. And the other metric is recommendation efficiency, and it is evaluated by the recommendation time. Now we are going to show the comparison of different methods on recommendation accuracy. So in this figure, the x-axis is the different recommendation methods. So the first 4 methods are differentially private LSH-based method. And the 5th method is the LSH-based method. And in the last is the non-private UPCC-based method. And the y-axis, the left y-axis is the MAE value, and the right y-axis is the RMSE value. So for MAE and RMSE value, the smaller MAE and RMSE of a method, the better recommendation accuracy this method can provide. So as we see, the non-private method UPCC always achieve the smallest MAE and RMSE. This is because this method is non-private and it needs get access to the raw data. For our differential private LSH-based method, we can see when the privacy budget epsilon increase from 0.1 to 10, the recommendation accuracy becomes better and better. And when the epsilon equals to 10, so which corresponding to the, in the fourth method, epsilon equals to 10, the MAE value and the RMC value are very close to the fifth method of the LSH-based method. So this means when the epsilon, when the privacy budget is big enough, our method can not only preserve similar recommendation accuracy with existing LSH-based recommender system, but it also provides differential privacy guarantee for the user data. And this figure shows the recommendation efficiency comparison of different methods. We can see the non-private method, UPCC, always have the highest recommendation 10, which means UPCC is the most inefficient recommendation method among the three recommendation methods. And the same, the first four methods are the differentially private LSH-based method, and the fifth method is the LSH-based method. And then we can see when the privacy budget epsilon increases, our differential private LSH-based method can achieve very similar recommendation 10 as the LSH-based methods. So this tells us our differential private LSH method can still preserve very efficient recommendation. So now I'm going to conclude and discuss about our paper. So the conclusion of our paper is we propose differential private LSH method to enhance the privacy preserving of LSH-based recommender system. And our DPLSH-based recommender system preserves high recommendation accuracy and efficiency while providing differential privacy guarantee for users' data. However, as we know, deep learning-based methods in recommendation system community becomes quite popular now. In this paper, we did not compare our differential private LSH-based recommendation system with the state-of-the-art deep learning-based recommendation system. The contribution of our paper is to enhance the privacy preserving of the existing LSH-based recommender system. I hope all of you enjoy this video. So if you have any questions, feel free to contact me. Thank you.